All right, in this last video, I want to go over some ways in which the Doppler effect has been used to make different discoveries, and it's got different sorts of usefulness. Probably most of you are already aware that the Doppler effect is used by police to determine how fast you're going, okay? And so that's what their radar gun does. It can be done with lasers as well. So the radar signal or the laser signal goes out, bounces off your car, and the bounce as it comes back is Doppler shifted because you're moving. And it's pretty straightforward to measure the amount of that Doppler shift and to get a pretty accurate measure of how fast you were going. Doppler effect is used in radar, okay, sometimes called Doppler radar. And so let me just talk about how that kind of works. Mostly when you see a radar image, it's something like the one here on the right. Okay, greens and blues, reds and yellows, that kind of thing. This is what's called a measure of the reflectivity of the radar signal. Okay, so which is pretty much what it sounds like, which is how much is being reflected back. And by knowing how much has been reflected back, they can determine particle size, okay, the nature of the particle. So they can tell if it's a big drop of water or a small drop of water or a snowflake, something like this. So they can see those things that way. Okay, now over here on the left, okay, you don't see this very often, but this has to do with the velocity. Okay, so Doppler radar is able to determine the velocity of the reflecting object. So these are pretty sophisticated systems that can not only tell you the size of the particle, if it's a big raindrop or a little one or whatever, or hail, but which direction it's moving. Okay, is it moving towards the radar or away from the radar or something like that? Okay. And those can be very useful because you can get these sorts of situations like this. So let's look in here. Okay, you've got a region where there's lots and lots of rainfall right there, and kind of a strange shape in there like this. Okay, and this is what's called a hook. Okay, in radar terms, that's called a hook because it has a hook shape. Okay, but if you look at the velocities, what happens, what corresponds to, is here's where all that intense rain is, right in there in the center. All right, but the red, these are all, I'm not sure in this particular image if that's towards or away, but let's say that's towards the radar, and the green is away, which means we have something going like this. All right. Now, when you get this sort of motion with the weather, that's called a shear. Okay. And you always get a shear before you get a tornado. All right. And in fact, what we're seeing here, this is both the reflectivity and the Doppler image of the hook that corresponds to a tornado that was in Oklahoma in 2011. All right. And so this is how you can spot a tornado using the radar before anybody can maybe see it on the ground. So it's pretty useful, a pretty useful tool. And if you know what you're looking for in the Doppler radar, okay, you can see these sorts of things. Okay, so let's talk about exoplanets. All right, exoplanets. So these are planets that are not in our solar system, okay? And hundreds of these planets have been discovered now, okay? And so let's talk about how we discovered those, okay? So let me just sort of talk about these images here. They show different sorts of Earth or planets, how they might compare to Earth in terms of their size and that sort of thing. And there's this index, Earth Similarity Index. I'm not an expert on that, and I didn't have time to kind of go look that up for you, but this has to do with the size of the planet and its distance from its sun, which gives us some idea of what surface temperatures might be like. Okay, so this is it's not an arbitrary scale, but it's very speculative. Okay, think of this as a kind of an educated guess about what that planet might be like. Okay, and so again, it's trying to get us some idea about habitability. Okay, what might the average climate on this planet be, its temperature, its gravity, those sorts of things. Okay. Now, this is an artist's rendition, and there is no basis for the pictures that you see here. Okay. They're just, someone's like, let's make this one more blue. All right. Okay. In terms of trying to determine how much oxygen or water is on a planet, that sort of thing, I would be extremely skeptical about any claims that come out that way. This planet has lots of water, that one doesn't. Maybe. Okay, so take any of that with a grain of salt. I'm not saying no, it's not possible, but I'm saying that's very speculative, okay? It's probably a lot of strategic guessing went into that sort of information. But what we're worried about here is, how do we figure these things out? How do we know that there's an exoplanet there, okay? Well, it's because when a planet goes around its star, all right, the star responds, okay? So we kind of tend to think, here's the star, and the planet's like, woo, 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 just like this. But it turns out the moving planet affects the star, okay? And so the star itself goes in a little tiny circle opposite of the planet, okay? So they're kind of like, if I can exaggerate, they're going like this, okay? And the actual center of the motion is between the center of mass for the planet and the center of mass for the star, okay? So they're actually going like this, all right? So the result is that planet is like, from a distance, it looks like it's wobbling back and forth, boom, 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 which means it's going towards us and away from us, and towards us and away from us, and okay? So the light from that star gets Doppler shifted up in frequency, Doppler shifted down in frequency, shifting up, shifting down, shifting up, shifting down. And with light, that shifting frequency, sometimes we talk about in terms of color. So when the frequency shifts up, we call that a blue shift, because blue has a higher frequency. If it shifts down when it's moving away from us, that's called a red shift, because that's a lower frequency, okay? So we see it shift blue, shift red, shift blue, shift red, frequency up, frequency down, frequency up, frequency down. And then astronomers have ways of determining the size of a planet, of a star, okay? And we'll get into that later in the semester towards the end, all right? So you can get a really good idea of the size of the star in terms of its actual physical size and its mass, both. And so then based on how that thing's wobbling, you can figure out something about the mass of the other object. Okay, so you can all those things can be worked out. All right, so what they do then, all right, take a look over here. All right, they use the Doppler shift to determine the velocity of the star as it's wobbling while it goes around. Okay, and then they see these patterns, all right, where it's periodic like this, all right, and so then they can determine what's the period of the planet going around it. And this example is pretty crazy because it's like about 4 days. All right, so a year on that planet is only 4 days. All right, so that's probably not a good prospect for colonizing. Okay, because the weather on that planet is probably going to be pretty crazy, and probably pretty darn inhospitable towards life. Okay, because it may mean that it's pretty close to its star too. I don't know for sure, but that's probably a very large planet as well, which would mean it has a lot of gravity. And so, you might land and you'd step out of your little spaceship and just be like stuck to the surface of the planet. Okay. That would be a bummer. Okay. But So hundreds of these exoplanets have been discovered using this Doppler shift. Okay, so they see that wobble, and from the wobble, then they can infer the mass, probably the radius of the exoplanet. Okay, that kind of thing there. So it's really interesting stuff. Okay, now if you look out at all the different galaxies that can be found in the universe, all right, there's a really interesting pattern to them, all right? And we'll talk a little bit more about how we know some of this stuff later on, but if you look at the light from the different galaxies, the light is redshifted, okay? Now, what we mean by that is that the frequency is shifted downward. So we might say, well, yeah, but how do we know what the frequency is? Well, it's because mostly when you look at galaxies, what you see is the light that's being emitted by hydrogen. Okay. Now, hydrogen has a very specific chemical fingerprint. Okay. That's its spectrum. All right. And so there's a pattern of colors that go with that spectrum, and you can see that pattern of colors. And it turns out, let's suppose my fingers like this represent that pattern of colors. All right. So any other galaxy looks like this. But the further away a galaxy is, it's like shift. It's like offset a little bit like that. And it turns out the further away the galaxy is, the more it's offset. Okay, so it's shifted into a lower frequency because it's moving away from us. And so we see this in galaxies called the galactic redshift. All right, and what's really strange is the further away a galaxy is, the stronger its redshift actually is, which means that the further away you go, those things are moving faster away from us. So we have this situation where everything that we look at in the distant galaxy, or in the distant universe, those galaxies are all, they're not all moving away, but 99.99% of them are moving away from us. I think there's a few oddballs that are doing something different, but the general trend, the way general trend, is that these things are moving away from us. And the further away they are, the faster they're going. Okay. I'm going to check my next slide here. Yeah. Okay. Now we can graph that velocity, and the first person to do this was a guy named Edwin Hubble. Okay. And he was the first person that noticed this and started to track it. And he noticed that if you plot the velocity of these galaxies against their distance, so velocity is a function of distance, you get this straight line like this. You get this straight line, okay? And so people tried to kind of figure that out. Why would this be the case? And the thing that explains it is this. Let's suppose I've got a galaxy here, 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 and here, and we're over here, okay? So we look, we see these things over here like this. Now, if the gap between all of these is increasing in the same way, watch what happens, okay? So we're here, the most distant galaxy is way over here, okay? So if I start to open up my fingers at the same rate, I get this, okay? And so it turns out if this one is moving away, let's say at 1 meter per second, this one is moving away at 2 meters per second, and this one's moving away at 3 meters per second, okay? Because each gap from here to here has to open up at 1 meter per second. So this guy ends up moving really fast compared to the others, okay? 3 times as fast, sort of like that. And so this is where the Big Bang Theory originated from. Okay. Now we're going to talk more in detail about this later on. We'll even talk about the origin of the name. Okay. But this Doppler shift with the red shift of the galaxies is what started the ball moving to realizing that the universe hasn't always been the way it looks right now. Okay. During Hubble's day. Okay. And even I'm talking about Albert Einstein, okay, Albert Einstein didn't like the idea of a Big Bang. He thought there was something wrong. Okay, and then turns out Einstein was wrong about that. We know that the Big Bang happened. Okay, but back in the early 20th century, the end of the 19th century and the early 20th century, the dominant idea was what we see in the universe now is what has always been there. Okay, so that the universe is eternal and unchanging. Okay, so to speak, like that. All right, and we'll talk about some more of those things later on, like I said. All right, so there we go. So I will see you guys next time. We'll be Zooming and we'll hit our next topic there, okay?